Hi guys. So welcome to our next module on transformation of functions. And this particular video is intended to be viewed, if you will, after you've already gone through the Desmos activity where you're supposed to play around with the sliders of A, C, and D and record all your observations about what the effects of those parameters are. So if you have not already done that, pause the video and go do it, because you need to have done that first. This video is just intended to kind of summarize what you hopefully saw, but really extend it into applying those transformations graphically when there is more than one transformation happening to a function. That is the main point of this video. So once again, go through the Desmos activity first, and then within the PowerPoint videos for this week, they're all super short, by the way. If it looks like it's a lot, I realize that because it does look like a lot. But once you get in there, each lesson is super short and they're just very to the point. So hopefully if you pinpoint certain things that don't make sense or make less sense than others, you'll know exactly what to go back and work on. And within the PowerPoints, there's other small, very short videos, not made by me, but hand selected by me. So even though I don't always make my own videos, I promise I only pick good ones. So you can go in there and watch those. But once again, this particular video is meant to just summarize, talk you through, and then extend it into applying them graphically. So let me do my little screen share thing here, and we will take a look. Okay, so this is the Desmos activity that you hopefully have already done. And when it's all said and done, the main takeaway message that, and they can be in your own words, descriptive wise in your own words, but the A value, hopefully what you saw is that your A value makes the graph either get more and more narrow. We call that a vertical stretch. Imagine like stretching a rubber band. That's kind of what you're doing to the graph. If your A value is above 1, you're stretching those vertical values. So again, that's the vertical stretch. Whereas if your A value is smaller than 1, you'll notice that the graph is widening out. So the word that we use for that one is a compression. Think about like a trash compactor. The way that it like squishes everything down and like flattens it, it compresses the objects. Imagine that you're like putting weight on this curve so that it's, the steepness of it, so to speak, is getting pushed down by you because you're compressing the graph. So if and when your A value is between 0 and 1, we call that a compression. And the other main takeaway about the A value is it affects the outputs and the outputs only. So hopefully that was one of your observations. But if you think about it notationally, that makes sense. At least I hope it makes sense, because your A value is on the outside of the function notation, the f of notation. A is on the outside, and the play on words has always existed, that when something is on the outside of the notation, it either is an output, or in this case, it affects the output. So I'm hoping that that also kind of makes sense and is resonating with the stuff we've learned previously. And then the other cool thing that hopefully you noticed about the A value is everything we just said with regards to stretching or compressing is also true on the flip side, the negatives. So if your A value is negative, well, then your outputs get reflected, negated. What used to be positive on the outputs is now negative on the outputs, or vice versa. And you'll see that on the graph that we do together here in a minute. But nonetheless, the whole stretching and compressing thing, it happens both in the positive realm and also in the upside down or negative realm. So again, hopefully that was one of the observations that you saw. So that's your A value. And then your C and D, hopefully you observed, were your shifters. Those are shifters. So we'll start with the D value because I think that was the first one that showed up on your document. So your observation for the D value was hopefully that it simply moves your graph up and down. vertically, up and down. That's it. It changes nothing else. The steepness does not change. Let me set my A value back to 1 so that we don't confuse ourselves here. My dog apparently says hi, by the way. So yeah, that's Lola. Where was I? Ah, yes, math. Okay, so the D value raises your graph up if it's positive, lowers it down if it's negative. Pretty straightforward, I'm hoping anyways. But let me just point this out once again, because I'm hoping that it's helpful and makes sense. And that is your D value affects the outputs and the outputs only. Only your Y values are changing when it lifts up, and only your Y values are changing when it lifts down. If you track these dots, this blue dot, for instance, has now risen up to be this red dot. And then this blue dot right here at the input value of 1 has simply lifted up to a new output value at 2.2, but the input didn't change. It is still at a location of 1. The inputs are not changing here. It is only the outputs that are either getting lifted or getting lowered. And again, play on words, the D value is on the outside, once again, of the function notation. It is not inside the parentheses. It's on the outside. And so I'm hoping that that helps you understand why it is only the outputs, once again, that are affected. In this case, they're affected in an additive way, right? We're not multiplying the values. We're not stretching them in a multiplicative manner. We are increasing or decreasing them in an additive manner. We're adding to the outputs, hence lifting them all up. Or we're subtracting from the outputs, hence lowering them all down. So that was the D value. And then the last one was the C value. Let me put my D back at 0 so that we don't confuse ourselves. There we go. The C value is the one that is probably the most confusing because yes, it moves your graph left and right, left, right, left, right. But what's weird about this one is the actual C value that is recorded ends up looking opposite in nature when you look at the formula itself. So like for instance, right now my C value is 3.2. But if I were to actually acknowledge the formulaic version of that, the formula would say X minus 3.2. You catching me there? The C value is 3.2. Where did my graph go? It went to the right 3.2 units. It definitely went to the right. The red graph went to the right. But formulaically, it would say minus. So it ends up behaving in a what feels like opposite manner. And the reason for that, by the way, let me just pick a whole number here so that we can hopefully make sense of it. So this particular graph, as you hopefully have noticed, is just a parabola. It's an x squared graph. We call that the parent function, by the way. The original function, we call that the parent function. And then the transformed function is, well, the transformation function, but the original is the parent. So anyways, this is a parent function of x squared. So if you look at your table values down here, f of x is just the typical parent function. If you square -5, you get 25. If you square -4, you get 16, etc. But the g of x is the transformed version of that graph. And so if I make my C value, I'm gonna make it just a 2 so that it's easier to track down. You'll see what I mean here in a second. But if I make my C value a 2, here's the way this ends up working. The original function, for instance, was 9, an output of 9 at an input of -3. You square -3, you get 9. Makes sense, parent function. But if you look at the g of x function, that same 9, if you will, does not occur at -3 anymore. No, it does not. That 9 now occurs at -1. So normally you square -3, you get 9. But in the transformed function, you're plugging in a -1 to make the 9. Now let me tie this together for you in 2 ways. first and foremost, can you acknowledge that -1 is exactly 2 units to the right of -3, right? So picture a number line. -3 is over here on the left, and -1 is exactly 2 units to the right of that, right? 2 units to the right. Now back up here to our formula and what's going on behind the scenes. Okay, well, once again, the C value is 2. That's because, yes, it is going 2 units to the right. But in the formula, right, why is it that -1 is all of a sudden producing 9? That's because formulaically, you'd have to subtract -1 and 2 to get the -3. It's not -1 plus 2 that makes 3. Remember, the parent function was -3 squared. It's -1 minus 2 that actually makes the -3 that we were originally trying to, track down, so to speak, in our parent function. Let me choose positives in case that's still confusing, because I'm talking about negatives and sometimes I lose my students when I talk about negatives. Let's try +3. Okay, normally you square 3, you get 9. Done. Parent function, 3 squared is 9. Well, look at the g of x graph. Where did the 9 go? Well, it's down here. It's exactly 2 steps down the graph. So for g of x, it's when you plug in 5 that you get 9. Okay, but wait, 5 squared isn't 9, right? 5 squared is not 9. So why in the world is 5 producing a 9? Well, that's because if your C value is 2, 5 minus 2 is 3. And yes, 3 squared is 9. So when you have a C value, in this case, that's 2, all of your values are going to shift over to the right 2 units to compensate, if you will, for the fact that the skeleton function is x minus that number. So the opposite behavior, it all comes down to essentially whatever your C value is, your function is accommodating that adjustment. Again, because 5 squared is definitely not 9. And yet, as you can see in the table, somehow 5 is producing a 9. Well, that's because if your C value is 2, then it's 5 minus 2. That makes the 9. So I don't know if that helps at all. If I've totally confused you, well then shoot me an email. We'll hop on a Zoom call and I'll do my best to explain it even more so. Of course, this is a lot easier to do in person. So I apologize that we're in this online platform right now, but it is what it is. Hopefully that makes a little bit of sense. So once again, your A value is your stretch factor or compress, could also reflect upside down. Your D value is your shifting vertically up and down. And then your C value is your shifting horizontally left and right. But again, the horizontal shift is indeed in the quote opposite direction as far as the value that you see on the page. If you see a -2 on the page, yeah, it's going to the right. Or if you see a +2 in the document or in the function, well, the +2 actually means to the left too.